This is a talk called From Laptop Builds to Advanced CI. This is essentially about my journey of the past 10 years. Formerly worked at Hinge as a senior staff engineer until this Monday, and I'm now open for work. So if there's anything you see here that you would like me to bring to your organization or project, I'm looking. So a little bit about me. Came here from Minnesota. That's where I live now. I work remote, or I do. And it's cold most of the year. There's lots of ice and snow about 6 months. Lake Superior freezes over, and there's just a lot of good winter sports there. And then the other half of the year, there's just beautiful nature, bald eagles and bears. And that's where I'm from. I've been doing CI since about 2011. I got to the point where I didn't know how to make unit tests, and I found a passion that I really wanted to learn how this worked and make it work well for both myself and my teammates and others. I joined Hinge in 2014 and built the Android app and led the backend team for a while. We went from solo dev to 24 Android engineers where I onboarded and mentored all of them. And yeah, actively looking for remote roles. So, what does this talk about? I'm going to take you on the journey of going literally from laptop builds, absolutely no CI, no Circle, no Travis, nothing, which is what I started with, to automating all the things, and then we're going to make it really, really fast. And how much faster? As of Monday, this is what our CI looked like. 3-minute runs for unit tests, 9-minute runs for release R8 minified builds, and UI tests in about a minute. We cheated a little bit. We only run one. For context, this is a semi-large project. There's 400 Gradle modules, 290,000 lines of Kotlin, 24 active contributors, constantly pushing a CI. We used Dagger Hilt. That was the only thing left with capped, otherwise KSP, and Gradle Kotlin scripts for the whole thing. So all the performance issues any of you have ever had with any of these things, you can get some wins out of this. The problems that we're going to be talking about is how CI itself and like the build process is distracting from feature work. So you don't really want to be working on this. You only want to be making the investments that you need to bring value to your project or team or business. CI also hopefully catches most, if not all, regressions. Actually, it doesn't catch all. There's nothing you can do about that, but this mitigates quite a lot of them. Lastly, if you don't have any CI and you're just doing laptop builds, you have a lot of security concerns just throwing key stores around that. It takes a month to recover from the upgrade process. Been through that, and it's not fun. So, this is our story. This is how every Android project starts. You have a laptop and a phone, and you want to put an app on it. And most of us go to the Google Play Store, and we say, or Google Play Console, make an app, and we say, hey, I just built this AAB file on my laptop. I'm going to drag and drop it over into the web interface for the very first time, upload that build. Wonderfully makes an APK that's so much smaller, and user downloads to their device. Wonderful. And they tell their friends, and they tell their friends, and they tell their friends, and then all of a sudden you have a lot of people asking for features. And even this like drag and drop process is just, you immediately like, no, I don't want to do this anymore. So this is distracting, and you write a little bash script with some Gradle plugin, maybe a triple T. We used it for years, and it's super wonderful, reliable, and open source. And you automate that from your laptop. Good. But then, the fun factor of success where you get another engineer joining, and then more. And then all of a sudden, you have not just the features that you're putting out through publishing through your laptop, but everybody else's. And so you decide, hey, I don't want this running on my laptop anymore. We need to put this on CI and get it out of my workload. Also, there's regressions happening. You're all committing to the same code base. The second there's more than one engineer on a project, you don't know everything that's going into it because you don't know the thought process that the person had when they were writing code. And there's also security concerns, like I was mentioning earlier. You don't want that key store that's hard to recover just floating around in Slack being copy-pasted. So we're going to walk through a couple CI solutions. And I'm doing light introductions to this part, and the fun advanced stuff is in about 10 minutes when we make it fast. But just to introduce you to CI, if you haven't ever done it before and you're coming from laptop builds like I did, we're going to be automating building and publishing, automating testing, and automating some security. At this point in the process, you should be asking yourself, what should CI look like before you go and make it? Because once you make it, it's a lot harder to change. You should be asking yourself, when do we build? Do we build on commit? Do we build on merge? Do we build nightly? If you use a merge queue, do you make changes for that? What do we run? Do we run unit tests? Do we run Android lint? Do we run UI tests that are really, really expensive and take a long time? Do we do self-hosted or managed? Mostly these questions should be answered by the people that are going to maintain it, hopefully, and not so much a top-down order, because the person maintaining it is going to have to deal with all the painful outcomes to all the answers to these questions. This talk is specifically going to focus only on builds on commit push. For automating security, I'm going to address that first, at least the most important things. You should be handling secrets appropriately. And what do I mean by that? That key store I was mentioning earlier, instead of hard coding it and committing it straight into your project and then whatever CI system you're using has that, and you can't rotate it out with like getting rid of it and then, oh, it's still in the Git commit history, so it's there forever. You should inject your secrets into every single CI run that you do, and therefore rotating them is independent of your code base. And you should not use any personal user tokens. I've done this. I'm sure everyone who has ever made a CI system has done this. And it's just never fun for the next person to come along and clean it up because everything breaks. So we want to just make a quick job to automate some testing on CI because publishing is a little more complex and tests, we run them all the time. So we're going to do that on commit. There's these verification tasks that are available to us. So we're going to try out test, debug, unit test. And if you start working on CI, you're going to be very familiar with YAML very quickly. So I just bang out this quick little CI script. And all it's saying is, I'm going to make a job called unit tests. I'm going to use a Docker node that uses a default Circle CI Android image. And I'm going to check out the code base. And then I'm going to run Gradle test debug test. I'm done, right? Well, when the tests fail, I get this wonderful wall of text that's fun to read, and it says there are failing tests. See this helpful report that you can't access anymore because the CI instance is gone. But I want this. I want the nice visual report that tells me what failed and what are the actionable outcomes. So I go back to my script, and most CI managed solutions have some way of making these reports available to you as long as you can get to JUnit output, and Android helpfully is JUnit compatible pretty easily. So you say you're going to store test results in a directory. But wait, first we need to do a couple things. One is we need to collect all the test results from all the modules. And two, we want to do that collection always, even on test failure, which is the whole point of getting them. So we create the directory that we're going to put them in. We find all the files that match a regular expression, and we copy them into test results, the destination folder. And because all of this matches up, you get the wonderful report. If you're not familiar with Bash, there was a really wonderful talk earlier in the conference about Android Bash shell scripts. Really advise you to check that out for references. So we did that. Now there's UI tests. And this would be the command that you run in order to actually run them. But we're not going to do that because running an emulator on CI yourself, especially starting out, is slow and flaky. And you just shouldn't do it. It's not worth your time. Until you're an extremely large project, or don't write them to begin with, or use a fast vendor. Both of these have a startup time of about 10 to 20 seconds. And that's how we got our UI tests down to about a minute for one test on commit, and that at least gives us the validation of, hey, the app didn't completely break from this change, which is really helpful because that's what you want. Otherwise, we got around it by just compiling our Android test sources, and that caught 90% of things that would actually fail in Android test anyway, or UI test. So we did that for testing, and we want to automate publishing. We want to do this because you want reproducible builds. You don't want someone's laptop to have to be configured in a certain way in order for builds to go out. The number of times I've heard a dev spilling water on their laptop, a cat walked onto it, they smashed the screen with a power cord inside, and then if that's the thing that you're building, the thing that the company depends on for product and revenue, like that's super, super costly, and you mitigate that cost. Also, this process, once you start scaling your team, you can hand this off to a release manager or anyone in your company, because all you need to do once you automate this is say git tag, and then it's done. So just the same process you were doing on your laptop, but in that CI script. The other things you should consider automating is KT-lint to ensure consistency in the writing and detect for code smells that are more complex than what KT-lint detects. These both have auto-formatters that can auto-format quite a lot of the mistakes that people make, and then everyone writes the same kind of code, and no one is spending time in code review talking about code nits or code smells. XML Starlet, to validate XML structure, it doesn't catch all the things that could be wrong with XML. There's actually some pretty obvious ones that it doesn't catch, but it runs so fast, and the things that it does catch, it's worth like the 2 seconds it takes to run. I'm not going to how to run these because all of these have excellent guides about how to do that. What I'm going to talk about next is we did those things to automate, like to get into CI world, and now we're starting to get these questions from our devs that are saying all this wonderful work is making them slow, but the whole point was to make them fast. So why is it slow? Well, we automated building and publishing, and we automated tests, we automated security, and everything you add into CI takes time. So we want to get it back to a reasonable amount of time. It's still going to take some time, but how much? And we're going to address scaling problems by using these different methods. We're going to be using caching, we're going to be using parallelization, we're going to use the merge queue, and we're going to do shadow jobs. This is what we want, but we need to get there. Or rather, that was the ideal that we were shooting for, and we eventually got to this. And we're going to focus on the unit test case for the rest of the talk, just because there's so many different experiments that I could go through, and there's not enough time for all of that. I'm going to be showing this graph repeatedly, and every change that we make, I'm going to be showing you exactly how much win we got from each change. And you can also see from my talk and from my slides how much work it took to get each change. Just to call out, the green stuff is Gradle, the yellow is Gradle configuration cache, and the stuff down below is Git and Docker time. So first, we're going to do the easiest thing you can possibly do in CI. It's cache dependencies, and the thing to cache is Gradle caches. There's roughly 4 of them. There's more, but these are the ones that I'm going to go through. There's the build cache, and this is essentially all the tasks that you're doing during the executing phase. There's the dependency cache, which is all the AARs, jars that you're downloading because of all the libraries that you depend on, Android X, from Maven Central and Google repository, whatever. Then, if you're doing Kotlin Gradle script, you're going to have a script cache. If you miss this, other things like the configuration cache won't work. The configuration cache caches everything that happens during the configuration phase. If you've ever built your project and noticed that it goes through saying initializing, configuring, and then executing, these are the phases that I'm talking about. So, just to start on CI, where we have right now in our story is there's only local support on your laptop because your build stays on your laptop day in, day out, but CI keeps getting recreated if you have ephemeral runners. We're going to focus on the dependency and script caches because those are really easy to cache. So if we look in the Gradle user home directory, we can see that in the home.gradle caches folder, there's a whole bunch of things. And there's some version folders and some things named build cache, journal, jars, etc. The dependency cache is in modules 2. If you cache that, and for our project, it was like somewhere between 400 and 900 megabytes. But the script cache is over in the version folders. So depending on what version of Gradle you're using, you want to be calling this out in whatever caching strategy you have. So I go back into my Circle CI config, and I add these 3 lines to my code base, or for CI pipeline. So these things are now remote supported. And by the way, don't worry, you don't have to take pictures. I'm going to have a slide towards the end. You should take a picture of that one. So we do this, and this is how much wind we got, just by going from control to this. There's also some overhead from saving the cache and restoring the cache, but obviously it's very well worth it. Now I'm going to go through a couple Gradle properties that are one-liner winners. None of these are defaults. Generally leave the defaults alone if they're in here. Surprisingly, these 2 are not defaults. They probably really should be. Gradle caching being true and parallel being true. If you don't have these on, you can't use the build cache that we're going to enable later. And also parallel, if you've modularized your app, like you're not going to get the parallelization build unless this is on. In Kotlin 1.7, use class path snapshot was introduced as a flag. Setting this on allows you to use their latest incremental compilation. If you're on Kotlin 1.6 or earlier, this is a good call out to your team and manager to be like, hey, we should really upgrade because wow, that was a long time ago, and just by upgrading, we can make things build faster. If you're still on capped, and hopefully we're going to get rid of, Hinge will get rid of it in a month, you could set capped incremental true, and that's been working decently well for us. Besides that, there's some build config optimizations you can do. You can set build features build config to false. It basically just stops generating build config for any module that is generated. It saved us about 30 seconds, which is not a lot of time, but since it's a one-line change, then why not make it and then multiply that time forever? Enable build config as bytecode. We didn't really see a significant performance difference on this change, but that might get better in the future. There's questionable IDE support depending on what Android Studio version you're in, and just from the number of people in this room, there's more Android Studio versions out there than there are people. So yeah, maybe be cautious in enabling this because this worked for us, but maybe not for you. R8 max workers is an experimental new flag. We did see a small win about this. By default is 1. And what this does is enables multiple R8 workers to do compilation during your minification phase. So there's not really worth to give it win, but we turned it on. Hopefully it'll get better over time. So those are the Gradle properties. Now, I often get asked, especially by non-platform engineers, where did I find these? Well, I just lurk in the Android X open source repository. They have some really excellent documentation about their Gradle properties. And since they're the people working on Android open source, they are very closely connected to the open source community of everything that's being developed that could possibly influence these. So this is a pretty good starting place. So we did that, and it got a little bit faster. Parallelization is the next thing that you could do, splitting up your jobs into multiple things, or maybe running your unit tests across multiple workers. And the only thing I'm going to say about this is the overhead cost, because there was a CI talk yesterday that covered parallelization. So just specifically about the overhead cost, between Git and restoring and saving the cache in Docker, if you optimize everything else, this actually becomes a significant percentage of your build, and it can be worth optimizing. We're going to cover that towards the end of the talk, as long as there's time, but it also depends on how you organize your pipeline. If you have every single job in serial, like one after the other, you're going to be paying this cost for your entire workflow run, and then your developer is going to be waiting the entire length of your workflow to get any feedback or like a pass-fail in the PR. Whereas if you run them in parallel, generally, as long as they're developing decent code, they should be getting pretty fast pass-fail feedback. So next question from my team was, main is failing, even though we passed CI. Right around 16 devs, if I remember correctly, we started noticing this. And part of it was that we were also making changes to CI while people were developing. So how did this actually happen? Well, if you have main going and you're working on your amazing new feature button, and you missed that there was a change in main that changed some shared behavior or changed the CI checks or added a regression that'll be discovered when future builds are run or flaky, then that can happen. How do you deal with this even though everyone's checks on all their PRs passed and now main is failing? You should really look into merge queue. Nowadays, it's super easy to just turn it on GitHub. It works great. It does introduce some inefficiency to your overall code review PR merging pipeline, because essentially every single PR now needs to run CI checks again, even if it was up to date with main. For a larger team, this is worth it. For a smaller team, it's not. So I wouldn't enable this until you get your first failure on main due to this thing. Caching build steps. So we talked about caching dependencies earlier. We're going to focus on the build cache from Gradle, and we're going to take this from local support to remote. And I'm not just going to add Gradle remote cache. I'm going to tell you how to optimize it as much as we did. If you look at a GitHub repository, Gradle Enterprise build validation scripts, you can run these experiments over and over on your project and understand whether or not there are tasks that are not cacheable. If it's not cacheable, then the build cache can't capture it, and therefore you have to compile a part of your code base again on your next build. The great thing about the remote cache is then you can share this with your team and also share it with CI. Generally, you want to modularize your project as much as possible. There are reasonable limits to this, and there's a much better talk about this than I can possibly give right now. Watch Siggy Johnson's talk about graph theory modularization. He gave it at DroidCon San Francisco last year, and he talks about between essentiality, measuring it, and using that to both look for regressions as well as what modules to target for modularization. So if you don't know if you're ready yet for this, that's a good talk to see, like, hey, like, if we even approach this, before we even write code, before we even try to modularize, because modularizing is hard. It takes a lot of time. That's worth checking out. I wish I'd seen it before we did modularization. Might have saved us time. Also, you should be observing Gradle build scans to observe performance for regressions if you don't have a measurement tool like that. And then the Gradle remote cache, there's a link up here if you want to take a screenshot of it, but this is the open source remote build cache node. Generally recommend 90 days, 300 gigabytes, and use validation scripts. It's going to take an infrastructure or SRE engineer to set this up in whatever systems that you have. So this is a not small investment to get running and also a maintenance cost going forward forever. Most local NCI runs will benefit from the build cache though. So once your team is roughly like 8 or 10 and you have a bunch of modules and you can start benefiting from the build cache, even locally, might be worth investigating whether to enable that and get it running. It's free, at least to run. Then there's Gradle Enterprise, which recently rebranded the other week to Develocity. Why would you pay for a tool if the build cache is free? They provide support for features beyond remote cache. They really help figure out failures, cache misses, and performance issues across a team, especially if you're not experienced with Gradle. Gradle is a pretty huge learning curve. I don't understand it nearly as well as one of my teammates at Hinge does, so yeah. And we were looking forward to using test prediction. Not exactly sure what we would get out of that yet, but we were looking forward to it. So build caches now got remote support. Great. That was a pretty dramatic win for us. So generally it is worth, for our project size, the effort that we put into it, and also the maintenance costs going forward, running the validation scripts either manually or eventually automating them, that would also be worth it for our project size. Is it worth it to use the latest JDK? Yes, 19 plus, hands down, because just doing that gave us another significant build performance. And all we had to do was go into our build scripts and say, use target source 19 and bump our Docker image that we're using up to JDK 19. By default, a lot of managed providers only support either Java 8 or Java 11 or maybe Java 17 for CI builds. So you would have to either make a Docker image yourself or build off of someone else's Docker image that is out there in open source. So we just talked about how upgrading to JDK would be great, but would JDK 19 work with our project? Is there anything we need to change? Like, how do we know before we put it out there, is it going to break on someone's laptop that's running Windows, or like, what's going to happen? Will X version of dependency Y work on our project? This is definitely an issue that we started running into in the past year. And generally, what seems to be the answer to this is shadow jobs, which Zach Swears wrote a really wonderful article about. Essentially, the idea is to run nightly checks against your project with the latest snapshots of new versions. This allows you to try out new tools before your team is thrown into the mix. If you've ever upgraded Android Studio and seen it just completely break, this is a decent solution to that. We've had multiple wins throughout the past year of not breaking developer environments and catching issues before they were rolled out to the team this way. But we actually ended up using it for JVM argument tuning because we were running into some memory limits with our CI provider. Disclaimer, I am totally not responsible for anything that you see in the JVM argument slides whatsoever. They're going to be completely different for every single project out there. First thing I want to say is the garbage collection algorithm trade-off. Each garbage collection algorithm makes a choice about what they optimize for and how much. And generally, this goes into three parts: transactions per second, the throughput, latency, the amount of time you spend in a garbage collection pause, and footprint, like how much memory is your build using, or JVM process. So you can kind of think of these as different points on a triangle, and that moving towards any one end of it makes a trade-off to the other two. Parallel GC and G1 GC are the two algorithms I'd like to talk about. They're relevant for anyone, I believe, on JDK 8 plus. I think G1 was introduced in 8 or 11. I primarily have been testing it, both of these on 19. And this is where these algorithms roughly land. I'm sure there's a better graph out there that actually has the right positioning, but generally want to give you the idea that parallel optimizes the most out of all the algorithms for throughput, and that G1 GC has a more balanced choices. Also, parallel has obviously more footprint and longer GC pauses, and G1 GC has lower footprint and shorter GC pauses. These differences are hard to see on any given build unless you do build without cache and rerun tasks and a whole bunch of other options when you're in your Gradle builds. You're not going to see significant differences between these two algorithms unless you run a lot of builds in that particular way where you don't use any of the caching whatsoever. Generally, parallel, great if your resources allow it. It is the fastest thing. You generally, on CI, you're paying for the resource, so you might as well use it. It's not like you get money back for the unused memory on your CI instance. That would be pretty cool. And G1 GC, use when resource constrained. It can save about 10%-ish or 5%, depending on your build and project, etc. If you're running into memory limits like we did, we opted into this for a while until we could get our memory usage under par in order to keep building. The Kotlin JVM arguments. So I've been saying JVM arguments in general. These are specifically for Kotlin. There's this older one, Kotlin daemon JVM options, and it has a whole bunch of disclaimers about like, hey, when passing arguments, do this and this and this. You don't have to read that, it's not important. There's this weird call out. This is relevant in a little bit. Arguments that come after a space will be used for Gradle daemon, not Kotlin daemon. That is documented. And then a whole bunch of other disclaimers of like, hey, if you use a recent JDK version, it'll be ignored. So they say, oh, use this other thing, which is newer and has way fewer disclaimers. Just use it and it works, except if you put spaces at the beginning of this. And I randomly ran into this, and it was hilarious because I was doing tuning thinking, why when I was like changing these things, I didn't see a change in result. If you see something and you're thinking it's impossible, it's definitely happening. So need to write into them and have an issue for that to get it documented. So JVM heap size. There's been some back and forth on this in the Java and Android community, especially about CI over the years. And everyone's like, I don't know, I just like throw some numbers in and hopefully it works. Max is the amount of memory it takes to compile, generally, your biggest task or module or whatever. If you run R8 minified or Android lint, that'll be probably the thing that uses the most memory, and you'll see a task use quite a lot for those. For most projects, yeah. The min value is, I generally would advise like somewhere between 80 and 100% of the maximum value. I've seen some projects opt for a little bit less than 100%. Been reading a lot of JVM articles, and it's not completely conclusive, but the heap only grows when a garbage collection happens at the beginning of a Gradle run using JVM. So when you set this towards the max, then you avoid those GC pauses during startup, and you save a little bit of time there. I just want to talk about how JVM heap size and modularization are related. I mentioned that whatever you need to have enough JVM heap to compile your largest task. So if there is a module somewhere in your app, home, settings, core, this is just like a stupid example, that is really huge, and maybe you have 100 modules, maybe you have 12,000 modules like Uber. If there's one module that takes 20 gigabytes heap, then A, you can't make more workers than you have available memory for, and B, that'll be the bottleneck for your entire build pipeline if there is a code change or build cache can't be reused. So that's why these two things are related. Metaspace. Been doing a lot of reading and research about this, and it's really fascinating and just kind of silly. So there's a Gradle default for max metaspace size, and it's set to 250 megabytes. But normally, Java leaves it unlimited by default, and there's reasons. Compressed class space size, which is part of overall max metaspace size, defaults to 1 gigabyte. So I don't know why the Gradle default setting there is for 256, because that seems low based on the compressed size. And I'm honestly not even sure like how that works yet. But the reason why they made a default is because Gradle can keep growing and growing and growing its metaspace size until you run out of space. And if you specify any JVM argument and not max metaspace size, it will default to unlimited. So just to illustrate, the compressed class space size is part of overall metaspace, and there's class and non-space class space list. Anyway, these options are also related to using compressed oops for objects and compressed class pointers. These two things are related. If you don't have oops on, you won't have class pointers. Oops is defaulting on to 30 gigabytes and less for a heap, which is hopefully most of you. if not most projects in the world for Android. And it just uses a little bit less per memory allocation or per registration. And it also restricts the overall heap size to 32. So what if we turn it off? Because like maybe it's faster without it. It's actually not for our builds. We turned it off as an experiment and saw everything get significantly slower. But I did notice that at some point in our iterations and Gradle upgrades and AGP upgrades that using OOPS with unlimited max metaspace doesn't max out and cause our Gradle daemon to disappear anymore. I think there's been some, obviously everyone's constantly working on memory management improvements. At some point, our project crossed the threshold where this doesn't happen anymore and we don't grow infinitely on max metaspace. Setting it to 4 gigabytes was slower than unlimited. So there's something else going on that the JVM is doing that Gradle has worked on in order to benefit from. So stick with the defaults. There is a default for metaspace, and we found in parameterized testing that a gigabyte of metaspace helps avoid early metaspace-related GCs. I mentioned earlier the min heap, making it much bigger, avoids early GCs just in the general heap. There's also metaspace-related heaps, metaspace-related GCs. The code cache is where the JVM stores its bytecode into compiled native code. This is important because if you don't have enough code cache, then Gradle cannot continue the build and you'll fail with a code cache error. So we generally want to set the reserved code cache size to the maximum amount that you need for cache bytecode. We ended up giving it 512 megabytes. It seemed to just have an easier time having code cache related GCs or having fewer of them. If you want to actually measure what you should end up using, you should be using this JVM flag called print code cache. That'll tell you how much your build actually ended up using. And then you can monitor this, measure it for regressions and other things. This is a really interesting one, softref LRU policy. And this has been called out recently, the past like 6 months, because someone wrote an issue on the Kotlin issue tracker measuring their build and performance and upgrading JDK 19. And they came across this parameter, defaults to 1,000. And it's the number of milliseconds to hold references for per megabyte of heap size. So if you have an 8 gigabyte heap, you're going to hold on to your soft references for 2 hours. I hope your builds are not 2 hours long, but that means that you'll hold on to this for the entire build. If you set it to 10, it'll be a minute. If you set it to 1, it's 8 seconds. For us, we ended up sending it to 1. That was the sweet spot. 0 was too low. Max workers. Once you've looked at these other things, you should also be looking at this at the same time, but until you optimize memory usage and like figure out like roughly generally where your heap should be, you shouldn't really look at max workers yet. Generally should be a few less than the number of performance cores that you have available. It's going to spawn like hundreds of threads per process, so each process will run quite a lot. This is the number of maximum active workers that will be allowed to simultaneously be doing work. It will also, even if you set this to really high, it will not spawn more workers unless memory heap requirements are met. So all the things that we've talked about before, code cache, metaspace, and heap, those have to be satisfied in order to make a new worker. So if you have a 32 gigabyte machine and you say the heap should be 20, you're going to spawn 1 worker, at least theoretically. JMalloc and TCmalloc, these are memory fragmentation. There's an issue with memory fragmentation, especially in large heap applications, and it's better to use a better malloc algorithm. These two were ones that we looked at. I only have data for JMalloc, and we didn't see any speed difference with JMalloc, but we did notice a 10% less memory usage, and that essentially translates into being able to use more memory for your compilation process or whatever else needs it, especially lint. So what did we actually pick? for JVM args. If you want to take a photo of this slide, go ahead. Again, disclaimer. Oh, wait, sorry, spoiler. What do we actually pick? Well, what we did was we used shadow jobs to parameterize our entire build. Every single JVM option I talked about was completely configurable. That took a lot of work. We intermitted our build with those as parameters. We ran the tests, and then we found out that this was the settings that worked best for us, generally on the higher end for all of these numbers. And I think it's important to note that the context of this project is what got these numbers. If you're a small project just starting out, there's no point in doing this whatsoever. The defaults should work. There are some JVM measurement tools that you can use in order to not just guess and check, which is what I did in the beginning. JCMP for measuring metaspace, and using that print code cache flag for inspecting what code cache size was actually used. And there's a ton of different CPU and memory research usage tools. I'm not going to go into them because there's just so many out there to pick from. So what did those optimizations get us? Pretty significant. We basically got like leaf node changes down to almost nothing for execution phase. And that's cool. But that's also 90% of what builds are going to be, is this. So for our project, we decided to attack configuration cache. In order to turn it on, you have to go to your Gradle properties and you set configuration cache true. And we set, and we followed essentially the Android X current properties that they have for ignoring file system inputs. There was a kerfuffle earlier this year where things weren't ready, and all of a sudden we're like, oh, we can't use configuration cache the way we expected anymore. So this is in place. That's a good list and resource if you're running into file system checks that you need to ignore. Eventually that will go away, so if you're using them, you should keep monitoring the issues that are related. I remember looking for configuration cache, like where is it? And the documentation says it's essentially not in the user Gradle directory, but in your project. It's under your .gradle folder inside your project, and the configuration cache is in the configuration cache folder right there. So that worked up until, for a while, off and on CI, because we didn't understand everything that it was depending on. And as of Gradle 8.1, encryption was added. So we asked Gradle support, and they basically said CI is not supported because of how much of our builds it was using and how important it was us to get it working. We just kind of hammered away at it. I started looking at configuration cache reports. I looked at all of the inputs across environment variables and file system entries and system properties. And if you want to find a report like this, it's in the build reports directory for your project, not inside the Gradle folder. And there's a configuration cache report that gets generated every time it can't use the configuration cache. There is a way to turn it on for all builds. Didn't get a chance to explore that yet. So tried it on CI, and we got this helpful error message that says calculating task graph as no configuration cache is available for tasks. And this was very confusing because we cached it. We put it in our CI cache. We know where we stored it. I SSH'd in the machine. It's there. When I ran the build a second time, it used it, and I was like, what is going on? So I talked to Inaki from Gradle back in DroidCon in New York City, and he said, you need to cache the encryption key, and it's in a different spot. So I looked through the Gradle changelog for the pull request that added encryption, and CC key store was the directory that it uses. So I was like, cool, that's a good piece of information. And I also saw there's a test that actually specifies the behavior that I was seeing. Calculating task graph as no configuration cache is available will happen if the key store is not available or missing. So Went into the CC key store directory, found these 3 files, cache properties, the lock file, and key store, cached it, and got the same message. I was like, that's confusing. And at this point, I did a little facepalm because there's some documentation that I had followed on Gradle's website that basically says you should clean the Gradle cache before you save it of any lock files or property files. If you'll notice, there was a lock file inside the configuration cache encryption, so I was deleting the file I needed. Got rid of that code. Doesn't seem to have any issue now or for a few thousand builds since then. Calculating task graph as blah, blah, blah. Mentions Gradle plugin. Okay, we have a folder called Gradle plugin. This is probably referencing our convention plugins. So I was talking to my coworker. There's a bug in Gradle for inline functions that they essentially have build script compilation avoidance issues. So we removed all of our inline functions from all of our build scripts. And then we ran into this error, which was could not load the value of patterns, blah, blah, blah. That wall of text is kind of intimidating. This is the things to pay attention to, is it's saying file system inputs, which means either something is missing or it's corrupted. And still referencing root project Gradle plugin. So we noticed that we had cache plugin descriptors for Gradle plugin. We weren't really sure what else to cache, but the entire directory is only 40 megs, I think. So we cached that. A couple more errors later, basically similar stuff. We ended up caching the jars9 and transforms3 folder. And by the way, if you wanted to take a picture of everything we cached, this is the time to do it. Give it like a couple more seconds for that. I'll put up a blog post in a couple days once I'm back in the States. And we got this wonderful message. We're using configuration cache. And this was our Gradle Enterprise instance, looking at all the builds that are on our main branch. And this is our mainline build minified with R8. And you can see like sometimes it was 10 minutes and sometimes it was 40. And then once we got this working, it actually went down to 8 on average. So it was a very significant win for us. I also got a wonderful Slack message from a coworker. He said how blazing fast the PR time was because it didn't just impact, the way it impacted jobs was that it had less overhead on Gradle Enterprise. It was hitting it less often because if we restored the configuration cache, there are things in dependency resolution that were also resolved that we're also hitting remote cache for. So everything in build cache is remote supported now. It's wonderful. And those 2 yellow things go away completely for those builds. Got a 6-minute build. It's great. But I want to make it faster. So we were relying on this is actually a year ago. We're relying on a big Docker image for Android. It's 2.5 gigs. And we noticed recently that our Git clone pulls were around 400 megabytes. Some binaries get committed. Once it's in history, it's really hard to pull out. A lot of investment to get that working. So let's just quickly solve these things. If you just delete things that you're not using in your Docker image, like we don't run emulators, we don't use anything older than the current API version for running our unit tests. So we were able to get it down to less than a gig. I'm pretty sure we can actually go much lower than that. Over here, the other 2 images, these are Alpine images that use, the JRE one uses Azul JDK19, and Bear is like no Java whatsoever. It's just super tiny. The download and extract time for these relative images are pretty much correlated with the size of the image. So if you remove things from your Docker image that are used in your CI pipeline, you'll get roughly get the benefit related to the size. We do use this Android image for all of our Android builds. And then for Git, we just looked at the Git clone and checkout size, and there's a really helpful guide on GitHub about shallow clones, and it mentions a couple different methods: no blobs, no trees, and shallow. Now, the time is also correlated with how much data you end up pulling with these different methods. We ended up selecting no trees because we also do a whole bunch of GitOps in different parts of our CI pipeline to do things like automated feedback and other things. So while shallow would be the fastest one, treeless meets our needs, and shallow also comes with a pretty heavy price and penalty for any additional Git operation. So we would get a speed improvement only to lose it later. So we do all that. We prune the Docker image, and that gets us this much. And then we do the clone optimization, and now we're down here. And this is present day. That's how we got to 3 minutes. And for R8 and UI tests, this is also what we were able to achieve. So just to recap everything we walked through, there's a lot, so hopefully this list helps keep it in memory. We did a whole bunch of caching. We pruned our Docker images. We did either treeless or shallow clone, whatever works for your project. We did some JVM tuning and compiler flags. And caching optimizations will have to be a future talk because partially I'm at time and partially the investment required for that was beyond my team's size. The only optimization you can really do is make the network traffic faster or like do non-ephemeral builds. And unless you're at a bigger size than we are, it wouldn't be worth it. Topics not covered in this, but also worth checking out. Local dev environment optimizations. Basically everything we did here also helps local dev environment, but there's some tweaks to it. It'll have to be a different talk. And then parallelization was talked about yesterday, an amazing talk. And there were 2 talks about automatic screenshot testing at this conference. So I definitely didn't want to do that. We have it in our pipeline, but yeah.